All right. So we just finished proving that the cardinality of the rationals, the cardinality of the natural numbers is the same cardinality. Now we're about to prove that the cardinality of the reals is strictly bigger than that of the rationals or the integers. So we know they're the same numbers. So how do you show that there are more real numbers than there are integers? It's not enough to say, well, because any two consecutive integers have an infinity of reals in between them, because that's also true about the rationals. And we already saw that the same number of rationals as there were integers. So that argument doesn't work. You have to show something more powerful. You have to show that no one-to-one correspondence between the real numbers and the natural numbers can possibly work, no matter how cleverly it's constructed. And of course, an infinite number of possible one-to-one correspondences, and we have to show that all of them fail. It's a proof by contradiction. You try to prove without a millionaire, right? So, assume towards contradiction that there was a one-to-one correspondence, that 1 corresponded to pi, and 2 corresponded to 1.00, and 3 corresponded to e, and 4 corresponded to the square root of 2. So all the reals were somehow listed in this table on the right column, and all the integers, the natural numbers, were listed on the left. Now it's obvious that all the natural numbers are on the left, 1, 2, 3, 4, and it's an infinite table, so they're all there for sure. Now, why is it impossible that all the reals are on the right-hand side, no matter how you arrange them? Well, because if they were all there, what you can do is go down the diagonal and construct a number that wasn't any one of them, and you do it as follows. You go down the diagonal, first of all, you can put a 0 and a decimal point, and then that 1 becomes a 2 here. And you keep going down the diagonal, and the second digit of the second number, the 0 here, becomes a 1 here. We add 1 to it. We add 1 to the entire diagonal. The 8 becomes a 9, and the fourth digit of the fourth number, fourth row, becomes 2 becomes a 3, the 3 becomes a 4, and so on. And that's a real number that we constructed by adding 1 to the entire diagonal. And that's a real number for sure, because there's the decimal point, there's a bunch of digits, there's a digit at the beginning, and in fact that real number is between 0 and 1. How many can see that? But that real number is not any one of the rows of the table. Yeah?
How do you know that's not a fraction of some sort of...
Well, it could be a fraction, but it's also a real number. I'm not saying it's irrational. I'm saying it's a fraction. It could be an integer. It could be 0.0000. It could be pi. It could be e. It could be 7. That's all I'm saying. Right. So, but what I'm saying also is that this number in red here is not equal to the first row, because it's different. It differs from the first row by at least 1 decimal place, and many others potentially. It's differing from the second row by at least 1 decimal place. It's differing from the third row by at least 1 decimal place, and so on. It differs from every row by at least 1 decimal place, and potentially many more. So it's not equal to any of the rows. How many can see that? By the way we constructed it. So no matter how we arrange the real numbers in this right row of the table, some are still missing. No matter how clever, how omniscient, how omnipotent we were arranging it, some are still not there. In particular, this one isn't there. So not all the real numbers are here, which means it's not a one-to-one correspondence. Some real numbers are missing from this assumed matching. And this matching is not a matching after all. It's not a one-to-one correspondence. Which means there is no way to put a one-to-one correspondence between the reals and the natural numbers. Any such attempt must fail by this diagonalization argument. That's the essence of diagonalization. Very, very powerful argument. It's a proof by contradiction. How many can see this? Any questions about it? It's subtle. But it's subtle. Yeah.
Isn't there something easier than this? More obvious?
Well, by all means. What do you suggest?
So here we're adding 1 to every digit.
Yes. By the way, if this digit is a 9, what will this be? A 0. In fact, do we have to add 1? Could we add 7? Could we add 2? Could we subtract 3? Yeah, that would work too. All you got to do is make sure that this digit and that digit are the same digit. There's lots of ways to accomplish that. Adding 1 works.
For example, for many entries in this table, by by adding a certain number we will actually just match it system. So
Well, but the point is, no matter how you arrange all the reals here, you can always find ones that are missing. Even if some omniscient, omnipotent entity created this table, and that's saying a lot. Right? I'm not going to mention any deities by name, I don't want to offend anybody, but pick your favorite. And even that deity fails to do this. Again, don't mean to offend anybody by saying what a deity can or cannot do, but this, it cannot. Things will still be missing. Now, I know what you're getting at. Now, isn't there some simpler way, more straightforward, more direct way of saying it? Let me try one. Let me say, well, of course there's more reals than natural numbers, because every two natural numbers have an infinity of reals between them. Like between 3 and 4, there's pi and many other things. End of story. Is that proof? Why not?
It's not a computation.
Because,
we don't have one correspondence argument.
but I'm not looking for a one-to-one correspondence. I'm saying one doesn't exist because between any two of these, there's an infinity of these, and so there's many more of this than this.
And then that's true for
But that's true for the fractions. For the fraction, we saw that they're the same already. So that cannot possibly hold water. It's not enough. So you have to be careful. And after 150 years of seeing, this is Cantor's proof from the 1880s. After 150 years of looking at this, we know of no simpler way of doing it. And this is not that, it fits on half a slide. So it's not that hard, not that long, not that complicated, right? So anything shorter than that would be a quarter of a slide or maybe one sentence. We haven't found such a sentence yet. Question?
how do you define more and the theorem?
Good question. What do you mean by more? There exists more of these than this. The cardinalities are not the same, and one is strictly larger. In other words, this set is certainly a subset of this set. The naturals are certainly a subset of the reals. For sure they are, right? A natural is a real, but a real is not necessarily a natural. Like 2 is 2.000, that's a real number. But a real number, pi, is not a natural number.
But if we use that argument for natural numbers and integers, then
Well, all I'm saying is that one is a subset of the other, a proper subset. So if they're not the same cardinality, it's clear which must be bigger. It's the one that's a superset is bigger than the one that's a subset, not the other way around. Right? So once we know which one is a subset, proper subset of the other, next we gotta show that they're not the same. And then one must be bigger than the other in this sense. So when you ask me, what do I mean by more? I just said, what I mean by more. That one is a subset of the other. Number 2, they're not the same cardinality. That one-to-one correspondence cannot exist. So we conclude that the cardinality of one is bigger than the cardinality of the other. Question?
You know that there are infinite numbers on the tables. How can you actually find x? Because there are infinites of infinites.
Well, I'm telling you how to construct X.
Yeah, so you cannot end constructing x. So how
No, I am constructing X. What do you mean? So you tell me that the first row.
when do we say that x has been constructed?
I'm telling you what the definition of every digit of X is. I'm saying that the kth digit of X is the kth digit of the kth row plus 1, modulo 10. So I'm defining X very specifically, very explicitly, unambiguously. Because you define the table for me. You come to me and say, this table is a one-to-one correspondence, which means you know what the table is. So you know what the first row is, you know what the second row is, you know what every digit of every row is. You come to me with that information, claiming it's a one-to-one correspondence. Then I come to you with this X, based on what you tell me, and show you that X is missing from your one-to-one correspondence, which means you can't possibly have a one-to-one correspondence that's correct, because X is missing. And there's many other things that are missing too. Can you give me a Y that's also missing? Sure, instead of add one, subtract one. You get a y that's different than x, and that's not there too. So we found something that's not there, but it's supposed to be there. You're the one that came up with the one-to-one correspondence. Presumably that works. I'm the one that's showing you why it can't work. So it's a proof by contradiction. And even if you had omniscient, omnipotent knowledge and power at your disposal, that wouldn't do you any good. Because you still come up with this table, and I still find a hole in it. It's a very, very powerful technique. It's hard to prove you're not a millionaire. Very hard. Think about how you would actually prove it to the IRS if they ever question you about that. Yeah.
Is it a problem where you have numbers that are like 0.9 repeating?
Ah,
It's the same.
good question. So what if this number here was 0.9999999? What's the mathematical value of 0.99999? Is it equal to 1 or is it almost 1? How many say it's almost 1? How many say it's equal to 1? Yeah, good. It's equal to 1. Why is it equal to 1? Why is 0.99999 equal to 1? It's equal to it, not almost it. How would you prove that?
Multiply it by 10 times.
Yeah, multiply this by 10, and so you get 9.999, right? This times 10 is this, right? And this times 10 is this. And subtract this from that. Right? So call this, call this x. Let's start with trying to figure out what this is. Call it x, so we don't presume it's 1. Let's call it x. So 10 times that is 10x, right? So if this is x, this is 10x. How many believe that? Okay. So now subtract this line from this line. So this minus that is what? 9. This minus that is what? 9x. So, x is 1. It's not approximately 1. It is 1. Right? So this brings an interesting point. This brings the point that representation in decimal, in base 10, is not unique. You can present 5 as 2 different ways to represent it in base 10. 5.0000 forever, or 4.999 forever. 2 different representations in base 10 of the same mathematical quantity, 5. Is there a third? A third representation of 5 that's not equal to the first 2 in decimal notation? How ambiguous is this decimal notation? Does it stop at 2? Or could you have a third representation, a fourth, a fifth, a 10th, all the same as each other in mathematical value? How many say 2 is it? I would say it could be 3 or 4. Interesting. Majority says. I'll let you think about that. For extra credit, tell me. I mean, the answer is either it stops at 2, or there's more ways to represent 5 or any other number in base 10. Is pi in base 10 a unique representation, 3.1415? Is this the only way to represent pi in base 10, or is there some other way? Yeah.
Are we talking about decimal format?
Yeah, it's a decimal representation. Because in other bases, all bets are off. Representation is very base dependent. Right? For example, if the base was pi, it'd be very simple to represent as just 1. If it was 2, it'll be a binary with zeros and ones, and that'll be a lot different than looking at this set of digits. And is there something special about base 10? Or could we use any base to represent numbers? Let me say you can use any base you want. Yeah. So why do we use 10? Because we had 10 fingers. If we were, sloths or something, we'd be using base 6 probably. Right? It's an accident of evolution and biology. Actually, some societies use base 20 because they use their toes also. I'm not kidding. It's true. In fact, some societies don't have numbers at all. of any base. How many heard about that? I'm not talking about some science fiction film, you know, in Middle Earth or something. Some societies on this planet, villages, they're you know, the Amazon forest or someplace, you know, out of the way. They don't have the concept of numbers whatsoever. Think about the deep implications of that. They can't count. They don't have the words for it either. So they can't say 7. And they can't say 12. What other implications follow from that? It's very, very deep and fundamental.
They share everything?
They must. Do they have money? No. Money is a way to count. If they can count, money is pointless. Because having $20 or rubles or shekels or, you know, is the same as having 10, is the same as having 30. They're all indistinguishable. They can't count. They can't own property either in terms of size and acreage. They cannot count. They don't have the words for it even. But let me say, they have perfectly fine lives. They're happy. They build fires. They tell stories. They raise children. They hunt and gather. They do all sorts of wonderful things, and they don't count, which means they have no salaries if they have no money. So they have no notion of buying and selling using a currency. They have no way of telling time. They can't say 11 o'clock, that's 11. They have no word for 11. They can say, well, let's meet when the sun is high in the sky. That's a different story. But they have no clocks or watches, which means they have no iPhones or computers either. All these things basically count every which way they turn. A computer has counters inside, registers that count. So they have no advanced technology, and they don't need it. They have perfectly fine, happy lives. Amazingly enough. How many heard of such a thing? Well, my gift to you. It's happening on this planet right now among some people. This is not some science fiction story. All right, so that means not only you can't take for granted that base 10 as opposed to something special, you can't even be taking for granted that counting is a valid thing to do or a necessary thing to do to have a nice, productive, full, happy, joyous life. Okay, but here we are back to this society. Here's a number that's not in the table. So that means no table can be complete one-to-one correspondence between the reals and the natural numbers. Yeah.
If this was in binary, would there only be one number in the table? Just like switching?
So you know, if this was in binary, would this X still work?
There would only be one.
Yeah. Will there only be one? Not necessarily. Could be many more than one. Yeah. So I just showed you one, but I can show you many others that would work too. What else? So let me ask you some questions. What if we took this X and put it in the first hotel room and moved all the guests one down? Well, is this table now complete? How many say yeah? How many say no, it's still flawed? Yeah, it's still flawed. Why?
It's simple.
You can pull a centric over on the new table, and you have another Y that's not in the table, and then another Z that's not in that table, and so on. So adding these missing things to the table ain't going to fix the table. There's so many holes in it. So this technique is so powerful, it makes end runs around all attempts at the situation. The situation is not fixable. Because if the table was fixable, this omniscient, omnipotent entity that constructed in the first place would have done all those fixes before they even presented it to us in the first place. And then it would be fine, but it isn't. That's another way of thinking about it. So there's no way to fix this table. It's fatally flawed, no matter what you do, which is kind of amazing. Now, how many have seen this argument before? One person, okay, good. So again, my gift to you, that's okay. That's what we're here for. And if this doesn't make you kind of edgy and uncomfortable and a little bit disturbed, you're probably not understanding this or thinking about this deeply enough. Because after all, when I first heard about this some 40 years ago, This was greatly disturbing. Kind of edgy, kind of unbelievable, kind of quizzical and challenging to the mind, and something you can meditate over for forever, and still not completely grasp why this is true, and why this isn't true about the fractions, the rational numbers, but true about the reals. Why can't you do this for the fractions then? Why can't you put the fractions in this table and then show that there's a fraction here that's not in the table, and therefore you cannot have a one-to-one correspondence with the fractions? Kind of 2 slides ago, when we showed a one-to-one correspondence between the naturals and the fractions. What's wrong with that argument?
It may not lie in the rational set.
This number that you construct here from the fractions will be a real number, but it's not guaranteed to be a fraction, to be a rational number. This number could be e or pi or some other irrational number. And then it doesn't belong in the table, so the fact that it isn't in the table is not a contradiction, it's fine. And the table can then still be a fine one-to-one correspondence. And we already know you can construct such a table from the 2 slides ago. You can turn this dovetailing, line into a nice long table. So there's that. Any other thoughts or questions? Yeah.
So is this proof, is analogy, is there analogy in other base, in binary?
You can do this in any base you like. So if this was in base 7 or base 2, same argument will hold. There's no way to put one-to-one correspondence of real numbers in base 2 with the natural numbers.
In binary, there's
In binary, this would also work, because a 1 here will become a 0, and a 0 here will become a 1, and this number will not be equal to any of the rows, and so it's missing from the table, and there's no way to complete the table for all.
But the thing is, like the first F1 isn't represented that way in binary. Like there's 1.0, 1.0. You cannot represent it that way.
Oh, you can represent any real number in binary, right? You can represent pi in just zeros and ones. Right? There's nothing special about base 10 for representing pi. Pi will not look like this in binary. It will look like a bunch of zeros and ones, but together they will be equal to pi in terms of their values, right? In fact, in your computer, you represent pi in zeros and ones anyway.
But there's a digit, like we have 128 digits.
Yes, but here we have an infinite number of digits.
Okay.
So we're not constrained by, there's no word size of 64 bits or 128 bits. The word size is infinite. So with a word size of infinite, you can represent pi in any base that you'd like, including fractional bases, if you think about it. You can represent pi in base 3.5. Or you can represent pi in base e. Or you can represent pi in base pi. Pi in base pi is 1. How many get that? What is a base anyway? Right? Whatever the base is, this is the base value, and this is the square, and this is the cubed, and so on. And this is 1 over the base, and 1 over the base squared, and 1 over the... That's all it is, right? It's multiples of powers of the base. And the digits are between 0 and the base minus 1. How many get that? That's what base counting is. And in base 10, this is the units place, right? And this is the tenths, this is 100th, this is the 1/10th, 100th, 1,000th. And there's a decimal point, and goes through 9. But it could be any base, including fractional bases, not necessarily whole numbers. Exact same principle. You have to worry about the digits exactly, between 0 and the base. But you can work it out. All right, let's go on. So x is missing from a table, so it's not matched to any natural number, and so that's a contradiction. So this is not a one-to-one correspondence. So this is a non-existence proof by nature, and specifically it's using this technique called diagonalization. And this technique we're going to get a lot of mileage out of in this course. there'll be dozens of problems where this technique will come and save the day. So remember that technique, wrap your mind very tightly around that. It's very important. That and one-to-one correspondences and dovetailing, those two techniques will get you a lot of mileage in this course. Induction won't. All right, so we already said, why can't you just insert X into this table and move everybody one down? Is because, you can still do the same trick and find yet another Y that's missing from the table, so that's not going to fix things. And we already talked about what if 0.999 and 1 are already in the table, because this could be 0.999 and this could be 1.000. So if this number is 0.99999, we already showed that 0.999 is already equal to 1, right? So it doesn't belong in the table because 1 is already there. So how do you fix that problem with this double representation of certain values in decimal notation? It's easy to fix. It's a hint. Well, what do you skip? Because you go down the diagonal like this and you get 0.9999, that could happen. And 0.999 is equal to 1, and 1 is already in the table in row number 2. So you haven't contradicted anything. So what do you do?
You don't have to follow the rules strictly to make it 9.
Yeah.
You can
Exactly. Avoid the 9s. So if this was going to be 0.9999 or any other kind of repeating 9s, just avoid it by making it a 7 or a 6 or a 3 or any other digit besides that digit. It's easy to do. How many see that? End of story. So now you don't have this problem anymore. So that's not going to save you either. This situation. We have multiple representation. By the way, the answer is 2. 2 what? Most. A real number can present 2 different ways in decimal. Not 3, not 7, or most 2. And most of them is unique. Like pi is unique, E is unique, and so on. The situation only happens when you have 0.9999 repeating. Not even 0.777 repeating. That's not a big deal. Think about it. Try to prove it for extra credit. Okay. So that's what diagonalization is. So, welcome to infinity. It's tricky business. A lot of your common sense everyday assumptions begin to fail when you deal with infinity. You have to watch your intuition very carefully because your intuition will lead you astray. Your intuition is geared to think about finite quantities, finite sets, everyday sets, not about infinite sets. The mind is not naturally geared that way. But after this course, it will be. You'll be able to think about infinities with facility, with agility, with ease and grace. All right. Now, a word about existence proofs and why they're hard. We already mentioned this, but let's have a slide on it for the record. Right? So non-existence must cover all possible ways of not being able to do something, not just one way it doesn't work. That's not enough. Right? So a counter example is not convincing for a non-existence proof. It's convincing for an existence proof. You show me an example, I say, okay, that works. Or show me a counter example and say, okay, that fails, end of story. But if I want to show you that nothing works, not just this thing, I'm showing you it's not symmetric between existence and non-existence. So we already said, if you want to prove that you're a millionaire, show me the money. Show me your bank account with a 7-figure salary, balance. Or show me your house. If you own this house on a private island, then it's really yours. Yeah, you're a millionaire. You can't get that for cheap. If you show me a big pile of cash in your basement, yeah, you're a millionaire. I mean, maybe a drug dealer, but you're a millionaire. That's the point. But how do you prove that you're not a millionaire? Could you show me a bank account with only $5 in it and say, okay, QED, I'm not a millionaire. There's my $5 in my checking account. Is that convincing? No. Maybe you have, cash stashed under your mattress. Maybe you have, some Bitcoin, in some strange account. Maybe, if you show me your house and it looks like a little shack like that, does that prove that you're not a millionaire? No. Maybe you just enjoy slumming it for whatever reasons. Car and it looks like this. Does that prove that you're not a millionaire? If you drive a $50 kind of junker? No. Maybe that's your hobby. Who knows? Maybe you like to do that. So it's hard to prove you're not a millionaire. In fact, essentially impossible to prove you're not a millionaire. Right? So existence proof and non-existence proof are not just symmetrically opposite, equivalent ways of proving and thinking about things. For existence, you have to show one example that works. For non-existence, you have to show that no example in the universe can possibly work. And the last proof about that is that was a non-existence proof. That's hard to do. It's like proving you're not a millionaire. It's not a symmetric situation. That's why non-existence proofs are so much harder than existence proofs. And if P is not equal to NP, which we believe it isn't, but we'll get into NP-Completeness toward the end of the course, proving such a thing will be very hard. Because it's like proving that you're not a millionaire. You want to show that there's no way to solve NP-complete problem using a polynomial time algorithm, and there's an infinite number of possible algorithms you possibly employ, and you need to show that none of them can possibly work. That's a tall order. That's hard to do. Okay. Any questions about that? Okay. So your Cantor came up with all sorts of amazing other insights. So here's a so-called Cantor set. It's one of the strangest sets you've done. So you start with a unit segment, 1 unit length. You remove the middle third, and then you recursively move the middle thirds of the segments that remain. So here you remove the middle third, you get these two segments. Then you remove the middle third of that, and you get these two. You remove the middle third of that, you get these two. And you keep doing this forever. The question is, what points remain in your set after this infinite process? And first you might be tempted to think, oh, nothing's left. But that's wrong. How many can see there's stuff left? What's left, for example? 0 and 1 are always there. Not only that, the beginning and the end of every segment are always left. So there's an infinite number of points that remain in the set, no matter how far you carry it, or even to infinity. How many see that? Okay. But the solid segment that remains, it's a cloud of points. It's a fractal. So the total length that you remove is 1/3, and then 2/9, a ninth here and a ninth here, and then 4/27, 1, 2, 3, 4, and you're removing all these lengths, and the total of all the lengths that you remove, if you work out this geometric series, is exactly 1. But the whole segment is 1 to begin with. So you might say, well, I have a segment of length 1, I remove the total length of 1, so nothing remains. Wrong. There's an infinite number of points that still remain, even though you removed the entire length of the entire segment, which is another weird non-contradiction. But there's no contiguous segment left. It's a cloud of points. It's a fractal. So it contains no intervals, but it's not empty, and it contains not just an infinite number of points, it contains an uncountable infinite number of points. So the countability of the integers is called Aleph 0. It's a countable infinity, because you can count it. 1, 2, 3, 4. The infinity of the reals is an uncountable infinity, because you cannot put it into one-to-one correspondence with the natural numbers, so you cannot count it. And it's a bigger infinity. This infinity of points left here is uncountable. You cannot put it into one-to-one correspondence with the integer, it turns out. You have to prove all these things. I'm just giving you the bottom lines here. So it's an uncountable number of endpoints remain, including, for example, a fourth. A fourth is in there too, in the remaining elements. And it's totally, and it's a self-similar set. So if you look at this set here, it's the same as this set. This set. How many can see that? It's a fractal. It has a fractal dimension of 1.58 something. Fractals have fractional dimensions. Most objects that you know and love have dimension either 0, 1, 2, or 3. If it's no dimensional or one dimensional or two dimensional like in a plane, or 3 dimensional like in 3D Euclidean space. But some objects have fractional dimensions. How many knew that? Dimensions don't have to be all numbers. And it's perfectly well defined mathematically. And fractals have fractional dimensions. So this set is a closed, totally bounded, compact, complete metric space with uncountable cardinality and Lebesgue measure 0. Try to say that 1 3 times fast. And nobody thought that sets like this existed. It never occurred to any human being up until the late 1800s when Cantor defined this. Very strange properties for a set. Right? So, kudos to Cantor for coming up with this. His name will present as a Cantor set. And you can cross the Cantor set, it's a one-dimensional set, with itself, and you get a two-dimensional Cantor set that's sometimes called Cantor dust. because now it's a two-dimensional set. It crossed with itself. How many know what it means to cross a set with another set? Cross product. S crossed with T is what? A set of elements, when S, a set of elements in T, to cross S with T, what's the definition of a cross product between S and T? It's not a trick question, it's a definition.
A comma B belongs to that.
Yeah, it's all elements from S, comma, paired with all elements of T in all possible combinations. How many understand that? It's a cross product, right? It's a cross. This is a Cantor set crossed with itself. So it's in 2D. So in that spirit, here's a Cantor omelet. You know, some pretty strange, and you can cross it with itself 3 times, and when you do, you get a Cantor sponge. 3-dimensional, so it's a Cantor set crossed with itself 3 times. And again, it has fractional dimension, it has all the properties of the one-dimensional version, except it's in 3-dimensional. And there's lots of other weird sets that you define with all sorts of strange properties. But we won't go too much farther into transfinite sets and transfinite arithmetic, which he pioneered. Math on infinite sets and arithmetic on infinite cardinalities. And I just showed you the tip of a giant iceberg. But these techniques will be used over and over and over again. Times. So now you have enough knowledge to solve all the problems in homework number 1, which is already posted on the website. So now we can go back in time and start with Aristotle again, and Plato. Right? So Aristotle lived in BC, 350 BC roughly, and he founded all of Western philosophy, which is most of what we know based on which is the basis of everything that came after that. In Eastern, in Asia, there were things all that, but they weren't as systematic in terms of rigorous science, and although some things were discovered in the East as well as in the West, independently over the centuries. We'll talk a little bit about that more. He was a student of Plato, a great student. Imagine how cool would it be to have Aristotle being your tutor. Yeah, that's pretty cool. And things are called Aristotelianism, or named after him. He developed a scientific method. By the way, what's a scientific method in one sentence? What do we mean when we say the scientific method, quote unquote? What are we referring to? Again, not a trick question, it's very straightforward. Yeah, you form some hypothesis, then what? You test it. How do you test it? Experimentation, observation, see how consistently it sits with other things that you know. And if it doesn't hold water, then what? Scrap it and do what? Iterate. Find another hypothesis. Cycle again. And I know it sounds simple, it sounds trivial, like what else would you do? Well, back in those days, people did all sorts of other things. Like somebody would get up and say, oh, I think this is like that. And I would say, oh, yeah, okay, yeah, he's right. Never questioning or testing. I know it sounds crazy, but this happens today too. Fake news. But I digress. Somebody says something and everybody jumps and believes it without really questioning it, testing it, looking it up, fact checking it. And that's not great, that's not good. Aristotle said, look guys, we have to put things to the test and make sure they sit consistently with other things that we know and they don't contradict them. And that there's no counterexamples that are obvious, and so on and so on. And then we can maybe live with that for a while until we find some other explanation. That's more sound, that's more reason, more rational, safer, and gets you more mileage and more progress. Without that kind of thinking, we'd never have iPhones or computers or jet planes or spacecraft or anything else of complexity or subtlety. So he pioneered this notion of gaining knowledge, right? And we call it the scientific method. It's hard to overemphasize the importance of that ethos when you seek knowledge. Everything is up for grabs. If it doesn't hold water, it has to go. It can't just stay in authority because somebody important said it, like a king or a pope or a politician or whatever. You know, it has to make sense, right? And only then we accept it and build on top of it and live with it and so on. And nothing is sacred. If something eventually is discovered to be inconsistent and not useful, then it has to go later, if not earlier. Okay, that's right? That's called rationality. It's called logic and common sense, and it's very, very powerful. Right? It's how we cure diseases. It's how we, build technology. It's how we prevent deaths. It's also how we deaths. Because that scientific method also allows us to create nuclear weapons and environmental disasters and all sorts of other things. So it's agnostic. It can be used for good or for bad, for help or for harm, whichever. Very powerful either way. Okay, so he wrote on every subject known to humanity at that time. He wrote treatises on all these subjects, on theater and poetry, on ethics, biology, aesthetics, on science. And he's the last person to ever know everything there was to know at the time that he lived. Today it'll be hopeless, right? We don't even, we can't even know our own niche in our own little subfield because there's so much to know. But at the time, there wasn't a whole lot known, and he knew it all. Yeah.
I'm just curious, like back then they didn't have paper. Where did they write it?
Yeah, well, they had papyrus, right, and scrolls and parchments, and sometimes good old stone tablets with chiseled, information.
How many of that would take to store those information? Like a room full of stuff. Did they ever?
So, how many heard of the Library of Alexandria? Okay, this was in ancient Egypt, and that library was in Greek times and in Roman times, and it had millions of manuscripts, parchments all rolled up, ordered by some way of cataloging them according to subject matter and author and so on, and there were millions of documents there. Basically, the sum of all human knowledge was there, and they stored it on papyrus and on scrolls and sometimes on stone tablets, literally etched in stone. Right? Sometimes we use colloquialisms. They would say, "Oh, this isn't chiseled in stone." Well, back then it was. On clay tablets. So yeah, knowledge was very expensive. Very few people can afford parchment. In fact, very few people could read. Even today in some countries, the literacy rate is abysmal. Anybody know what where the United States rates in literacy rate among the other nations of the world? Are we in the top 10? How many say, yeah, we're in the top 10? US of A, America. No, we're not, actually. Internet connectivity, we're not in the top 10 either in terms of availability or speed. Sorry, I love this country, don't get me wrong, but so was very expensive back then. You have to be really rich to afford a book, really a parchment, or a papyrus scroll, or whatever it was. But there were places where these things were gathered, very few. So the Library of Alexandria was the Google of the day, back in 200 BC. Unfortunately, it was ransacked, destroyed, and burned to the ground. And when that happened, much of the world's knowledge was lost on that one day. Because many of these books were one copy. There were never a second copy. Some guy would write some treatise after years of thinking or decades of contemplation, and the library got a hold of that, stored it, and when it burned down, that knowledge was lost. So some books we only know about by name because they were mentioned in other ancient scrolls. Some of them we don't even know about, we'll never know they existed, sadly. Today, so much stuff is recorded that in 1,000 years, people will know what you had for lunch this morning because you put it on Snapchat or Facebook or whatever. So now we kind of recorded probably too much stuff. But back entire wars happened, entire nations rose and fell, and we don't know a thing about them because nobody bothered to write it down. And if they did, that knowledge was later lost, and too bad. Which is bizarre. How civilizations to us. not just what somebody had for lunch 2,000 years ago on a particular day. Of course, that's false too. Okay, so even Bernard Russell, which is a giant thinker in his own right, we'll talk about him separately, said that almost every serious intellectual advance has had to begin with some attack on some Aristotelian doctrine. So even if you disagreed with Aristotle, you still had to mention it, because first you had to state what he said so that you could then disagree with it. Either way, you had to mention it. So he's probably one of the most well-cited people in all of history. There's actually a living person that's in the top 10 most cited people in all of history. He's alive. Anybody like to guess who he is, Mike? Erdos? No. He wrote 1,000 papers, but outside mathematical circles is not very well referenced or cited. Take a wild guess.
Maybe still living.
He's still living. He's a professor at MIT, actually. It's a hint. A lot of his courses, we already saw his name in the slide. This big Venn diagram, Chomsky, Noam Chomsky. He's like the seventh. He's the most well-cited living person today. Number one, living person. Among dead people, I think he's number 7. And by dead people, I mean Aristotle, Socrates, Shakespeare, and Jesus Christ. These are some of the other in the top 10. And he's number 7. He's still around. But anyway, so amazing influence. Aristotle appears on currency. He appears on stamps. So I'm just showing you a few examples. Paying to his contributions. Inventing the scientific method and a great number of other things. And here he is with his teacher, Plato, and he appears in the center of this famous painting, right? And there's the two, Aristotle on the right and Plato on the left. By the way, where is this painting appearing at UVA? Campus where there's a giant size version of this painting. Close. It's Capitol Hill, and it's a life-size, it's big wall mural copy it up here. Of course, we don't have the original copy. We just have a copy. Take a wild guess. And what is this painting? Okay, so now we're getting to art appreciation here. So this is the School of Athens, right? Who's the artist? Raphael, not the Ninja Turtle, but the Renaissance painter, 1800s, early 1500s, and it's the School of Athens. Actually, there at the Sistine Chapel in the Vatican, where there's the original on the wall. We actually painted it right on the wall. So this is me with the original. The other one was the Capitol Hall version. So I thought that was pretty cool. All right. Anyway, here there's a moon crater on the moon named after Aristotle. It's 87 kilometers wide. So talk about impact of these people, on cheese, and of course these are impact craters on the moon. So a lot of these people have moon craters named after him, and rightly so. Now it's not to say that Aristotle was correct on everything. There's a lot of things he got wrong, right? I mean, back in Greek days, they thought the periodic table has 4 elements, right? Water, earth, fire, and air. That didn't serve in terms of chemistry, right, or medicine for that matter. So later we upgraded the periodic table to have 100 and some elements, and that was a lot better, useful model for chemistry than the 4 elements that the Greeks were thinking about. But still, a lot of things he got right. And the point is, he said that if something is not right, we should jettison it and abandon it and chuck it and move on to better things. That was very, very important, right? Because many other thinkers and institutions don't allow that. They don't allow for their doctrine to be falsifiable or possibly wrong. In fact, they call it heresy or blasphemy. They completely reject the idea that it could possibly be wrong. That's very dangerous. That's how genocides and Holocausts and world wars get started. Somebody refuses to admit that they're wrong and think they're absolutely right and everybody else is off kilter. Very dangerous mindset. But I digress. Euclid, contemporary of Plato and Aristotle, basically founded all of geometry. In fact, it's called Euclidean geometry after him. The axiomatic method. What is the axiomatic method? What does it mean to use the axiomatic method for something?
Using some set rules for groups.
You have some rules, right? What are they called? Axioms. And you have a lot of them, and are they complicated? No, you have a few of them, and they're simple. And based on those axioms, you start putting them together and get some theorems and corollaries and lemmas and consequences and conclusions drawn from these axioms. I know it sounds simple, but all of mathematics and all of science is based on this method, like the axiomatic method. Right? And his book called Elements is the oldest and most impactful textbook. It's translated into over 2,000 editions into every language there is. Right? Even more so than the Old Testament. And unified math and logic, right? And he introduced rigor into thinking and reasoning. At the time, it wasn't obvious. People made assertions and other people would just believe it as is without any proof or without any testing. And again, I know it sounds off kilter, but even today this happens. So certainly 2,000 years ago, it happened even worse. So influenced basically every other scientist and thinker, mathematician, and rational person that came after him, including Copernicus, Kepler, Galileo. I mean, all these people were intellectual giants in their own kind, in their own way. Galileo and Newton and Einstein and Lincoln and Euclid was the hero of all of these people. And of course, all these people, us, right, for their country. Even Lincoln, Abraham Lincoln, U.S. president in the 1800s, at some point in his life, when he was young, he went into seclusion with his book and studied it cover to cover and reconstructed all the proofs and was able to prove some new things on his own and trained himself in rigorous analytical thinking before he even went into politics, and of course, the rest was history. Lincoln also came with his own proof for the Pythagorean theorem that was not known before. And there's dozens of proofs known for the Pythagorean theorem. So Lincoln was, pretty astute guy. So here's a cover of his treatise called The Elements, right? And it was translated into Latin and many other, Greek, into many other languages. And still very interesting reading today, right? And here's a piece of it on parchment. You asked me what did books look like back in those days. Here's what a book looked like in those days, at least one page of a book, like on parchment paper. And here's, in fact, this is from the Elements treatise, and here's showing some, in Greek, ancient Greek, some geometric constructions. So that's what a book looked like back then, right? And in that painting that we saw earlier, there he is in the lower right-hand corner doing some compass construction. So there's Euclid in that, and it's interesting exercise to determine who the other people in that painting are. So as a side issue, try to. So speaking of straight edge and compass constructions, here are some Euclidean straight edge and compass constructions. And for extra credit, tell me what each one of those are. These are the Platonic solids. Have congruent faces. So one made of triangles, and actually two more made of triangles, one made of cubes and one made of pentagons, and none are made of hexagons, not in 3D. In 4D, there's a couple of more Platonic solids, but it gets more convoluted. So for example, let's take this construction here. What does it do? Just from looking at the animation, what is the
Midpoint.
bisects a line, finds a midpoint on a segment, using all these straight edge and compass. So for extra credit, tell me what these other constructions are. And these became classical Euclidean geometry. Right. So again, he gets a lot of street cred for doing all these things. And how many have seen Euclideans of geometry before? A few of you? Okay. Here they are. Right? There's only a handful of them. They're pretty simple. Any 2 points can be connected by exactly one straight line. So here are 2 points. There's exactly one straight line between them. Not 0 lines, not 3 lines, 19 lines, one straight line. It's the first axiom. Second axiom, any segment can be extended indefinitely into a straight line. So a segment could then be extended into a unique straight line if you extend it indefinitely. I know it sounds simple. You got to say it. Otherwise, maybe it's not true. So a circle exists for any given center and radius. So if you're given a center and a radius, it's uniquely determined as a circle in the plane, of course. All right angles are equal to each other. What else will they be equal to? And the parallel postulate. This one is the longest and the least obvious. Given a line and a point off the line, there exists exactly one line passing through that point, parallel to the first line, which is not intersecting the first line. So you don't have. So if you have a line and a point, only one line passes through this point that is parallel to the first. Not three lines, not zero line, one line and one line only. Look how much longer that is than the first four. And most of these propositions and these treatise elements, the first 28 propositions, only rely on the first four axioms. Only later, for a few things, does he require the parallel postulate. And that made people think in later centuries that the parallel postulate is not even necessary as an axiom, that it's a consequence of the first four. And they tried to prove the fifth on the basis of the first four, and therefore render it unnecessary as an axiom, but rather make it a theorem. Now, why would you want less axioms in your axiomatic system rather than more? Why don't you want redundant axioms that are a consequence of the first few? Occam's razor, very good. Occam's razor, what does Occam's razor mean? Simpler is better. Less moving parts. It's more thrifty. It's more elegant. It's simpler, it's less complex. It's easier to understand, easier to manipulate, easier to change, dissect, modify, improve. A machine with fewer parts in it is better than a machine with more parts, all things being equal. That's why an electric car is much more efficient and effective than an internal combustion engine car. It's much fewer moving parts, right? And same thing for mathematical and philosophical systems. The fewer moving parts there are, all things being equal, as long as they accomplish the same job, understanding the universe around us, allowing us to build iPhones and spacecraft and jet planes, fewer moving parts is better. Right? So, for many centuries, almost 2,000 years, people tried to prove the fifth from the first four, and they failed. And only in 1868, 2,000 years after Euclid, 20 centuries, somebody showed that the parallel postulate is independent of the other axioms. What does it mean for an axiom to be independent of the other axioms? It means something very unusual. It means that you can take it in the positive, assume it's true, and your system will still remain consistent as long as it was consistent before. Or, alternatively, you can assume that it's false and take that as an axiom, and your system will still be consistent, assuming it was consistent before. You can take it either way you want. It's independent of the other axioms. It cannot be proven or disproven from the other axioms. And it took 2,000 years to finally prove that. And so it's an essential part of Euclidean geometry. And the way people try to prove it is by taking it as false and trying to show a contradiction. And that would have meant that it has to be true, which means it was a proof that it was true from the other axioms, and therefore it wasn't necessary. But all it did is gave rise to non-Euclidean geometries. So for example, if you try to say that given a line and a point off that line, there's an infinity of lines, all passing through that point, all parallel to the first, which is what can happen if your manifold is a hyperbolic space. You don't get a contradiction, instead you get a completely consistent geometry, except it's very different than regular geometry. Sum of triangle angles is less than 180, where in a plane it's equal to 180. Different triangles have different angle sums, where in a plane all triangles have the exact same angle sum, 180. Right? And triangles with the same angles have the same area. In hyperbolic geometry, that's not true. Excuse me, in the plane it's not true. In hyperbolic geometry it is true. If a triangle has the same angles as another triangle, they have the same area too. You don't have this proportionally larger and smaller triangles with different areas but the same angles. And there's no similar triangles in hyperbolic space. And it's completely, perfectly valid, self-consistent geometry, and the contradiction was not discovered. Instead, the geometry was so useful that Einstein based his entire theory of relativity on this geometry, not Euclidean geometry, but hyperbolic geometry. So this became from an exercise in trying to prove parallel postulate being independent of the axioms or being provable from the other axioms into an entire new geometry that then Einstein built relativity theory over and came up with the famous E is equal to mc squared and the rest of it. And for relativity theory, that was the basis for nuclear fission discovery and the development of nuclear weapons. And nuclear weapons is what essentially ended World War II very dramatically. And so the validity of this hyperbolic geometry was demonstrated extremely dramatically twice in 1945, one at Hiroshima and one in Nagasaki, unfortunately. But it started with Euclid and the parallel postulate that led to these two sad days where it's the only two times that we nuked somebody in a hostile situation. So I wanted you to see some of these connections, and we'll see many other connections as we go through this historical arc. You know, let's talk about the axiomatic method, the scientific method, axiomatic systems, the axioms of geometry, the parallel postulate, and attempts to prove or disprove the parallel postulate led all the way to very dramatic effects in world wars. You know, it wasn't just something abstracted, mathematical that had no consequence. On the contrary, it had the most severe consequences imaginable, right? And for many decades, we even live even today, we live in the shadow of World War III and the potential other, next World War with nuclear weapons. Nowadays, it's North Korea, it's Iran, it's other countries that are seeking to get nuclear weapons. And all this was only possible because of this, for better or worse. You can argue, either way, but the point is it's very dramatically connected to Euclid's axioms in this chain of events. So I want you to appreciate how impactful these things are on human history and understanding the world even to this day. It's not just some abstract thing that is a thought exercise. It's so much more than that. And of course, if you allow no parallel lines between that point and that line, you get another kind of geometry called spherical geometry, and there you have another set of interesting properties, which I won't bother to completely go through, but it's very different than either Euclidean or hyperbolic geometry, and there's many other geometries besides. But we used to think that the universe around us, this place here, which we inhabit, is Euclidean in nature. It's not. Einstein showed that it's hyperbolic. Space-time is a hyperbolic geometry with masses and gravitational fields and so on. So it turns out that, we used to think that the universe is Euclidean, which it isn't. It's actually one of these alternate geometries, hyperbolic geometry in particular. How many knew that? It's not a Euclidean universe. Okay, now you know. Another one of my gifts to you. Redefine your universe for me. Of course, it's not my gift, it's Euclid's gift and Einstein's gift and all the people that came in between. So again, very, very impactful insights, all going back to the scientific method and the axiomatic method. And there's hundreds of, even thousands of books on non-Euclidean geometries, entire courses in college on it, and people doing research on it even to this day. And it's a very flourishing field. It turns out Euclidean geometry is not one of the more useful ones. These other ones. But we didn't know about it for over 2,000 years. But without Euclid, we wouldn't even have Euclidean geometry, much less these geometries that basically rose out of trying to negate or refute or prove Euclidean geometry was the real one. And ironically, it isn't. Right? And the two people that are responsible for diverging from Euclidean geometry and coming up with hyperbolic and spherical geometries, and then many others, are Bolyai and Lobachevsky back in the early 1800s, late 1800s, on which works Einstein built his theory of relativity. And so, there's even some humorous puzzles based on non-Euclidean geometry, right? So, person leaves their home, walks 1 mile south, then 1 mile west, and sees a bear. Then he walks 1 mile north and ends up back in the house. The question is, what color was the bear? White, because where can this happen? North Pole, like you're going 1 mile south from the North Pole, then 1 mile west, then 1 mile back north, and you make a triangle on the sphere. Right? It turns out that the North Pole actually doesn't have polar bears, they only exist in the South Pole. So how would you fix this riddle? Right? So there's the tour triangle near the North Pole. There are some bears, just make sure they don't follow you back to your home, because you can have some awkward moments with these bears, especially if they're hungry. But where else can it happen besides the North Pole? That's not the only solution, it turns out. So this is like the first solution people think of. The equator. You don't go 1 mile from the equator, then south, then 1 mile west, and then 1 mile north. You won't end up in the same place anymore. South Pole. You can't go more south than the South Pole, so not quite the South Pole.
A mile above.
A mile above the South Pole? Then you're going south 1 mile, you'll end up at the South Pole. Then how do you go west from the South Pole? You can't. So again, not quite. Close. Try. So here's the South Pole.
South Pole is the center of the triangle.
So a circle around the South Pole whose circumference is 1 mile. Where would you start to make this true?
North 1 mile.
1 mile north of that. So you start 1 mile north of a circle whose circumference is 1 mile. So you start here, you go down, then you go 1 mile all the way around, then you go back north, and you end up in the same place. How many solutions are there?
Infinite.
Infinite. Any point around this circle that's 1 mile up from this circle will work. But there's more solutions yet.
Like circumferences that are not like half.
Yeah. So take a circle here around the South Pole where it's 1 mile twice around. And 1 mile up from all that is yet another set of solutions on this smaller circle that's twice around. And more families of solutions. There's an infinite number of infinite families of solutions. How many see that? And that's a much more sophisticated answer than the first. Correct, because the bears there are white. And there are bears there, actually. So in a Google interview, remember this one. That may get you an extra salary. And if you get that question right, you learned it here. Well, all you have to do is give me 10% of your salary. It's a good deal for everybody. Which also proves another point. So when you solve problems, always think deeper about solutions. Always think about alternative solutions, about other ways of looking at, other ways of solving it, more elegant solutions. Don't just stop when you get an answer and walk away like you won the lottery, because there's always ways to go deeper and more insightful and generalize things. And in this course, we'll do a lot of that. Okay. Any other questions or comments, thoughts? All right. So remember, the readings are due every Monday, but do them even before then. Don't save things for the last minute. Don't procrastinate. Solve lots of problems. Look at the problem sets. The first homework is already posted. Some interesting questions about infinities and cardinalities. And we'll have a fun time. See you then.